In a vast corner of the Milky Way galaxy, more than 4.5 billion years ago, a swirling cloud of dust and gas began to collapse under the force of gravity. This contraction marked the beginning of a new star, one that would eventually become our Sun. As the Sun ignited, a powerful source of light and energy was born, sending shock waves through the surrounding cloud of material. With the Sun's formation, it began to capture smaller particles and debris within its gravitational reach, creating a young and chaotic solar system. In this swirling disk of gas and dust, tiny particles collided and stuck together, gradually growing into larger and larger bodies. Through this process of accretion, the early building blocks of planets started to take shape, including a small, volatile protoplanet that would eventually become Earth. However, this early Earth, often called proto-earth, was far from the life-supporting world we know today. Instead, it was a fiery, molten sphere, frequently bombarded by other bodies in the solar system, with no oceans or atmosphere as we know them. As proto-earth grew, so did the disturbances in its orbit. Other young planetary bodies shared its path around the Sun, some of which would cross into proto-earth's path. Among these bodies was a Mars-sized protoplanet now referred to as Theia. Theia's trajectory would eventually bring it into a colossal collision with proto-earth, a collision that would forever alter the future of our solar system and lead to the birth of Earth's closest companion, the Moon. Chapter 1. The Proto-Earth Emerges. In the early days of the solar system, the process of accretion, the gradual gathering of particles through gravity, dominated the formation of planets. As the Sun's gravitational pull began shaping the surrounding cloud of gas and dust, tiny grains of cosmic material collided, stuck together, and formed clumps. Over millions of years, these clumps grew into larger bodies, becoming the precursors of planets, or planetary embryos. One of these growing bodies was proto-Earth, an early molten version of the Earth we know today, which had yet to acquire the stable surface, atmosphere, and oceans that make our planet unique. Proto-Earth, still in its infancy, was a chaotic and volatile sphere. Constantly bombarded by meteors and asteroids, its surface remained molten and unstable. Each impact added mass, heat, and energy to proto-Earth, allowing it to grow larger and increasing its gravitational pull, which in turn attracted even more cosmic debris. The building blocks of minerals and metals essential to life were already present within the proto-Earth, though they remained locked within its molten core, where gravity had drawn the densest elements, such as iron and nickel. Over time, as proto-Earth grew in size, its own gravitational field grew stronger. This enabled it to clear its orbit of smaller bodies and draw more material into itself. The accumulation of mass and energy led to intense internal heating, and proto-Earth's interior became a churning sea of molten rock and metals. These elements began to separate based on density, a process known as differentiation. Heavy elements like iron and nickel sank toward the center, forming proto-Earth's core, while lighter silicate materials rose to form a primitive crust. This early stage of Earth's formation set the foundation for its structure and magnetic field. However, proto-Earth was far from a stable, mature planet. Its surface was a fiery, unstable landscape of molten rock, broken up by volcanic activity. Without an atmosphere or water, the surface was bombarded by solar radiation, making it an inhospitable world. The forces at work inside proto-Earth caused constant volcanic eruptions, releasing gases that would later form a primitive atmosphere. This early atmosphere, rich in hydrogen and methane, was much different from the breathable air of modern Earth. As proto-Earth grew larger and hotter, its environment continued to attract other bodies that shared its orbit. These neighboring planetary embryos, remnants of the material that had failed to become full-fledged planets, drifted nearby in the solar system's early days. Some were large enough to exert gravitational influence on proto-Earth, disrupting its orbit and even altering its shape through gravitational forces. One such body was Theia, a protoplanet about the size of Mars. Theia's path around the Sun brought it increasingly close to proto-Earth, setting the stage for one of the most dramatic events in planetary history. As proto-Earth continued to stabilize and grow, its path and Theia's intersected, drawing the two planets closer over time. The precise reasons for Theia's collision course with proto-Earth remain uncertain, but the two bodies' gravitational forces inevitably brought them closer. While proto-Earth had become a larger, molten planet, Theia was relatively solid, with its own distinct materials and composition. The collision between these two bodies would be nothing short of catastrophic. Finally, after millions of years of approaching each other, the fateful moment arrived. Theia collided with proto-Earth at an oblique angle, a massive impact that would forever change both bodies. This giant impact hypothesis suggests that the collision was a glancing blow rather than a head-on collision, which meant that while a significant amount of material was ejected, both proto-Earth and Theia survived in some form. However, the energy released was immense, creating temperatures hot enough to vaporize rock and metal. The impact tore apart Theia, scattering its materials and leaving behind a vast field of molten rock and vaporized elements. A significant portion of this ejected material formed an orbiting ring of debris around proto-Earth. This material, comprised of fragments from both proto-Earth and Theia, would eventually coalesce into the Moon. The intense heat from the impact also remelted proto-Earth's outer layers, reshaping its surface and mixing the two bodies' materials together. Over time, the debris from the impact began to gather into clumps. Gradually, these clumps grew larger and formed into a single, stable body, what would become the Moon. This process, known as accretion, occurred relatively quickly in astronomical terms, with the Moon taking shape within tens of millions of years after the impact. While the Moon's early surface was molten from the energy of its formation, it would eventually cool, solidifying into the familiar form we see today. This monumental collision did more than just form the Moon. It also had profound effects on proto-Earth. The impact altered proto-Earth's rotation, increasing its speed and creating a significant axial tilt. This tilt, which continues to give us seasons as the Earth orbits the Sun, was one of the many lasting effects of Theia's impact. Furthermore, the ejected material that formed the Moon contained a mixture of proto-Earth's and Theia's elements, giving the Moon a similar composition to Earth's outer layers. This moment in Earth's history, where proto-Earth collided with Theia, marked a turning point in its journey to becoming the Earth we know today. The impact gave rise to Earth's Moon, a companion that would play an essential role in shaping our planet's environment. The Moon's gravitational pull would help stabilize Earth's axis, creating a more predictable climate and enabling the conditions necessary for life to emerge. Through the cosmic forces of gravity and collision, the young Earth transformed. In the violent, fiery aftermath of this impact, Earth and Moon were born from the remnants of two planets that had collided in a chaotic dance of creation and destruction. The Earth, scarred but strengthened, was now on a path of stabilization and transformation. Over the coming eons, it would cool, develop oceans, and acquire an atmosphere capable of supporting life, while the moon settled into orbit, forever bound to its sister planet. This is the story of proto-earth, a story of heat, collisions, and a fateful encounter with a wandering world that would ultimately give rise to the Earth-Moon system. The hero's journey of Earth had only begun, but the formation of the moon would ensure that it had a steadfast partner in its path through the universe. The presence of the moon would shape Earth's tides, stabilize its axis, and prepare it for the development of life in ways that were yet unimaginable. Chapter 2. The Great Impact, the Birth of the Moon. The collision between proto-Earth and Theia was one of the most cataclysmic events in the history of our solar system. This massive impact was not a simple crash, it was a cosmic collision of incredible force, forever altering the destinies of both proto-Earth and Theia. The collision transformed proto-Earth from a young, volatile planet into a world ready to develop oceans, an atmosphere, and, ultimately, life. And out of this fiery chaos, the moon was born, a silent witness to Earth's journey and a partner in its orbit through space. The impact itself was immense, releasing an amount of energy equivalent to billions of nuclear bombs. Proto-Earth and Theia collided at an oblique angle, with Theia striking Proto-Earth's surface at a high velocity. This angle of impact, rather than a direct head-on collision, allowed for both bodies to survive in some form. But it also meant that the collision released massive amounts of debris into space. Temperatures soared, with much of Proto-Earth's surface vaporized upon impact, creating a halo of molten rock and gas that enveloped the young planet. As Proto-Earth absorbed much of Theia's mass, its own structure was profoundly affected. The collision added a significant amount of mass to Proto-Earth, altering its rotational speed and tilting its axis. This axial tilt would have a profound influence on Earth's climate and seasons, creating a rhythmic cycle of changes as the planet orbited the Sun, a cycle that continues to this day. Proto-Earth's rotation also sped up, setting the stage for a faster day-night cycle than what it had previously experienced. Above this newly formed planet, a ring of debris now orbited Proto-Earth. This ring consisted of ejected material from both Theia and Proto-Earth, scattered across space as a result of the impact. It included fragments of rock, vaporized metal, and vast amounts of dust, all mixed together in a chaotic cloud encircling Proto-Earth. Over time, the gravitational forces of Proto-Earth acted on this debris, causing it to gather and coalesce, slowly forming clusters that would eventually give rise to a single, stable satellite, the Moon. This accretion process, though quick in astronomical terms, took tens of millions of years to fully stabilize. As debris clustered, it formed large chunks that merged through repeated collisions, creating a central body that grew in size and density. Gradually, these chunks coalesced into a single large mass, the early moon. Initially, this young moon was still partially molten, heated by the energy of its formation and the constant impacts of additional debris that continued to be pulled in by its growing gravitational field. The newly formed moon was much closer to Earth than it is today, appearing as a massive presence in the sky. Its proximity exerted a strong gravitational force on proto-Earth, leading to significant tidal effects that would shape Earth's surface and oceans in the future. The moon's gravity began pulling on proto-Earth, creating the first tidal forces that caused Earth's molten surface to bulge and shift. These forces would play an essential role in Earth's geological evolution, stirring its interior and contributing to the development of a magnetic field. As the moon cooled, its surface solidified, forming a crust that would bear the marks of its turbulent formation. This crust was scarred by craters, the result of impacts from smaller bodies and remaining debris in the aftermath of the giant impact. The moon's surface eventually stabilized, its craters and basins frozen in time, recording the history of its violent beginnings. Meanwhile, Earth itself was also undergoing dramatic changes. The energy released from the impact with Theia had caused proto-Earth's surface to remelt, creating a global ocean of molten rock known as a magma ocean. This molten surface began to cool and solidify once again, forming a new crust over time. Volcanic activity was rampant, releasing gases trapped within the planet's interior, which contributed to the formation of a primitive atmosphere. This early atmosphere, primarily composed of water vapor, carbon dioxide, nitrogen, and methane, was much different from the breathable air we know today, but it laid the groundwork for the atmosphere that would eventually sustain life. The newly formed moon also had an effect on Earth's rotation. As it orbited the planet, the gravitational interactions between Earth and the moon created a phenomenon known as tidal locking. Over time, this process caused the moon's rotation period to synchronize with its orbit around Earth, meaning that one side of the moon would always face Earth. This phenomenon, known as synchronous rotation, explains why we only ever see one side of the moon from our vantage point on Earth. In addition to tidal locking, the gravitational pull of the moon began to have a stabilizing effect on Earth's axial tilt. Without the moon's presence, Earth's axis would likely have wobbled erratically over time, leading to extreme shifts in climate and seasons. The moon's stabilizing influence helped keep Earth's tilt relatively steady, which in turn created a more predictable and moderate climate. This stability became crucial for the development of ecosystems, as it allowed for consistent environmental conditions over long periods, an essential factor in the eventual emergence of life. As Earth and the Moon continued to orbit the Sun, they settled into a stable gravitational relationship that would endure for billions of years. The Moon, now fully formed and gravitationally bound to Earth, became Earth's closest companion. Its influence on Earth's tides, its role in stabilizing the planet's axial tilt, and its impact on Earth's geological processes would prove essential to Earth's journey as a planet capable of supporting life. While the Moon's presence marked a profound transformation for Earth, it also served as a reminder of the cataclysmic collision that had brought it into existence. The shared materials between Earth and the Moon, particularly the similar composition of their outer layers, provided evidence of their common origin. In essence, the Moon was born from Earth itself, a fragment of the planet's past reshaped by cosmic forces into a separate, yet eternally connected, celestial body. In the aftermath of the giant impact, Earth began to evolve into a world that would one day be capable of sustaining life. The Moon's formation marked the end of proto-Earth's violent creation phase and the beginning of Earth's transformation into a stable, life-supporting planet. The Moon's gravitational presence would shape Earth's tides, influence its climate, and provide a source of light in the night sky, a silent companion on Earth's journey through the cosmos. The formation of the Moon stands as one of the most significant events in Earth's history, a moment when destruction gave way to creation and chaos led to order. Together, Earth and the Moon would continue their journey around the Sun, their destinies forever intertwined in a cosmic partnership that began in a fiery collision. This partnership would help shape Earth's evolution, preparing it for the emergence of oceans, atmosphere, and, eventually, life itself. With the Moon's formation, Earth had taken a major step in its hero's journey, a journey that would continue as the planet cooled, developed oceans, and began to create the conditions necessary for life. The Moon's influence, like a guiding force, would help stabilize and nurture Earth, setting the stage for a new chapter in the planet's evolution. Chapter 3. The Earth and Moon settle into orbit. With the Moon now firmly established as Earth's closest companion, the two bodies began to interact in ways that would profoundly shape Earth's environment and future. The early Earth-Moon system was vastly different from what we see today. The Moon was much closer to Earth, appearing as an enormous, bright object in the night sky. Its gravitational pull was even stronger, generating massive tidal forces that stirred Earth's surface and oceans, setting the stage for a dynamic planetary environment. As Earth and the Moon orbited around the Sun, they gradually settled into a stable relationship. This process, however, took millions of years, during which gravitational forces worked to balance the orbits and rotations of both bodies. The Moon's gravitational influence was crucial in this stabilization. By pulling on Earth's mass, the Moon created a tidal bulge, an elongation of Earth's shape, where the closest side of the planet was pulled slightly toward the Moon. This bulge wasn't only in Earth's oceans, but extended through its land masses, creating a slight deformation across the planet. These tidal forces created by the Moon had a profound effect on Earth's rotation. As the Moon pulled on the tidal bulge, it generated friction that gradually slowed Earth's spin. In the earliest days of the Earth-Moon system, a single day on Earth was much shorter than the 24-hour day we experience now, likely lasting only a few hours. But with each orbit, the Moon's gravitational pull slowed Earth's rotation little by little. This gradual lengthening of Earth's day continues to this day, albeit at an incredibly slow pace. In addition to altering Earth's rotation, the Moon's gravitational influence also caused it to slowly drift away from Earth. Every year, the Moon moves about 3.8 centimeters farther from Earth, a process that began as soon as the two bodies settled into a stable orbit after the impact. In the early days of the Earth-Moon system, this drift was much more pronounced, creating a cosmic dance as Earth and the Moon adjusted their distances to find equilibrium. As the Moon moved farther away, its effect on Earth's tides decreased slightly, leading to a more stable tidal cycle. This movement away from Earth was accompanied by another critical phenomenon: tidal locking. Tidal locking occurs when one body's rotation period matches its orbit around another body, causing it to show only one face to its partner. Due to the powerful gravitational forces between Earth and the Moon, this process eventually synchronized the Moon's rotation with its orbit around Earth. As a result, we now only ever see one side of the Moon from Earth, a side marked by dark plains and bright craters that has become familiar to us through observation. While the Moon's position was gradually stabilizing, Earth itself was undergoing significant changes. The planet's molten surface, left in a chaotic state after the collision, was slowly cooling, forming a thin, solid crust. Volcanic activity continued, releasing gases trapped within Earth's interior. These gases contributed to the formation of a primitive atmosphere, primarily made up of water vapor, carbon dioxide, nitrogen, and methane. This early atmosphere, while not breathable, laid the groundwork for the complex layers of gases that would one day support life. As Earth's surface cooled further, the water vapor in the atmosphere began to condense, forming the first oceans. Rain fell continuously for thousands of years, creating shallow seas that spread across Earth's surface. The formation of these oceans was a milestone in Earth's journey toward habitability. The Moon's tidal forces acted on these young oceans, creating strong tides that stirred the waters and played an essential role in the distribution of nutrients and minerals. The tides generated by the Moon's gravity were much stronger than they are today, causing the early oceans to rise and fall dramatically. These tidal forces helped mix the oceans, dispersing essential chemicals and minerals that would later contribute to the formation of organic molecules. This mixing process was crucial in creating a stable and nutrient-rich environment, a foundation for the chemical processes that would eventually lead to life. The Moon's stabilizing effect on Earth's axial tilt was another essential factor in Earth's path to habitability. Earth's tilt, the angle at which it leans relative to its orbit around the Sun, is responsible for our planet's seasons. Without the Moon's influence, Earth's tilt would likely vary wildly over time, leading to extreme shifts in climate. However, the gravitational pull of the Moon helps to keep Earth's tilt relatively stable, creating predictable and moderate seasons. This stability was critical in allowing Earth's environment to support a diverse array of ecosystems. As Earth and the Moon continued to orbit the Sun, their relationship settled into a rhythm that would remain consistent over billions of years. The Moon's orbit became more circular, and its distance from Earth gradually stabilized. With each passing year, Earth's rotation slowed ever so slightly, and the Moon drifted farther away. The two bodies had found a cosmic balance, creating a stable environment in which Earth could continue its transformation into a life-supporting planet. This early period of stability allowed Earth's geological and atmospheric processes to advance. Volcanic eruptions continued to release gases, adding to the atmosphere and influencing its composition. The young oceans, stirred by powerful tides, became cradles of chemical activity, where molecules mixed and recombined in endless combinations. In the shadow of the Moon, Earth was slowly evolving from a fiery, volatile world into a stable planet with oceans, atmosphere, and the potential for life. Through this cosmic partnership, the Moon had become more than just a satellite. It was Earth's stabilizer, a force that shaped its environment and protected it from drastic changes that could have hindered the development of life. The Moon's influence extended beyond the tides, helping to maintain a steady climate and contributing to the rhythm of days and nights that would become essential to the biological cycles of future life forms. With its gravitational pull, the Moon continued to sculpt Earth's surface and oceans, leaving an indelible mark on the planet's evolution. In many ways, the Moon served as Earth's cosmic guardian, providing stability and balance as Earth prepared for the next stage in its journey. This relationship, forged in the fires of a cosmic collision, would prove to be one of the most enduring and influential partnerships in the solar system. In the vastness of space, Earth and the Moon were now bound together, each shaping the other in subtle but profound ways. The young Earth, with its cooling crust, growing atmosphere, and swelling oceans, was on the brink of a transformation that would set it apart from any other planet in the solar system. And at its side was the Moon, silently guiding Earth on its path, a steadfast partner in its journey through the cosmos. Chapter 4: The Cooling of Earth and the Formation of Oceans. As Earth and the Moon continued to orbit around the Sun, Earth began a period of dramatic cooling and transformation. The energy released from the catastrophic collision with Theia had left proto-Earth in a molten state, but over millions of years, its surface began to cool and solidify, forming the planet's first stable crust. This process marked the beginning of Earth's journey toward becoming a life-supporting world, a journey that would see the formation of oceans, a primitive atmosphere, and the foundation for chemical processes that could one day lead to life. With the surface cooling, Earth's crust gradually solidified, creating patches of stable ground across the molten seas of magma. This early crust was thin, fragile, and prone to breaking, as the internal heat from Earth's core continued to push molten rock toward the surface. This period of volcanic activity would shape Earth's surface, constantly reshaping it, breaking it apart, and creating new land. Volcanic eruptions released vast amounts of gases, including water vapor, carbon dioxide, nitrogen, and methane, which were trapped within Earth's molten interior and now escaped through volcanic vents. These gases gradually accumulated, forming a primitive atmosphere around Earth. This early atmosphere, however, was vastly different from the one we know today. Instead of oxygen, it was dominated by water vapor, carbon dioxide, and other gases released by the planet's volcanic activity. This atmosphere was thick, heavy, and toxic, making Earth's surface an inhospitable environment. Yet, despite its harshness, this early atmosphere was a crucial step in Earth's evolution, as it provided a protective layer against solar radiation and helped to retain heat, aiding in the planet's long-term stability. As Earth's atmosphere thickened, the planet's surface continued to cool. This cooling allowed water vapor in the atmosphere to condense and fall as rain. For the first time in its history, Earth experienced rainfall, an event that would last for millions of years. The rain fell continuously, filling low-lying areas, carving rivers and streams into the crust, and forming the planet's first oceans. These early oceans were shallow and acidic, but they covered vast stretches of Earth's surface, creating a new environment that would one day be essential for the development of life. The formation of these oceans marked a turning point in Earth's journey. The water not only shaped Earth's surface but also played a crucial role in moderating its climate. As sunlight warmed the oceans, water evaporated, rose into the atmosphere, and fell again as rain, creating a cycle that helped regulate Earth's temperature. This water cycle became a fundamental feature of Earth's environment, contributing to a stable climate over geological timescales. With the oceans in place, Earth's surface underwent further transformation. The moon's gravitational pull created strong tidal forces, causing the young oceans to rise and fall dramatically. These tides stirred the waters, mixing minerals and nutrients from Earth's crust and distributing them throughout the oceans. The tidal action of the moon was essential for creating a dynamic environment in the early oceans, promoting the mixing and circulation of water and nutrients that would be critical for the future development of complex chemical processes. As the water cycle and tidal forces shaped Earth's surface, volcanic activity continued beneath the oceans, where underwater volcanoes released minerals and gases into the water. These hydrothermal vents, hot springs on the ocean floor, created unique environments where minerals and chemicals interacted in ways that were impossible on land. The extreme heat, combined with the rich mixture of chemicals, produced conditions that would eventually lead to the formation of organic molecules, the building blocks of life. This environment, a combination of oceanic tides, volcanic activity, and mineral-rich waters set the stage for the emergence of complex chemistry. Over time, the interaction between Earth's oceans and atmosphere helped to regulate the planet's temperature. Carbon dioxide, released in vast quantities by volcanic eruptions, dissolved in the ocean waters, reducing its concentration in the atmosphere. This process, known as carbon sequestration, helped to cool Earth's climate by removing carbon dioxide from the atmosphere, allowing the planet to maintain a more moderate temperature. This balance between the oceans and the atmosphere became a self-regulating system, providing a stable environment conducive to further chemical evolution. The cooling of Earth's surface, combined with the presence of a stable atmosphere and oceans, created a planet vastly different from the molten, volatile world of its early years. Now, Earth was a planet with a rocky crust, vast oceans, and an atmosphere that shielded it from harmful solar radiation. The Moon's gravitational influence continued to stabilize Earth's axial tilt, providing a predictable climate that allowed the water cycle and tidal forces to remain consistent over long periods. This stability would prove essential for the complex processes that would eventually give rise to life. As Earth settled into its new state, its oceans became rich with dissolved minerals and nutrients from the surrounding land masses. Over millions of years, the constant churning of the tides and the chemical reactions occurring at hydrothermal vents created a unique environment where complex molecules could form and interact. In these mineral-rich waters, molecules combined and recombined, forming increasingly complex structures that would one day lead to the emergence of organic life. In essence, Earth's cooling and the formation of oceans were the final steps in preparing the planet for the potential of life. The oceans, stirred by the Moon's tidal forces and enriched by volcanic activity, created a dynamic environment that would serve as a cradle for life's earliest building blocks. The atmosphere, although still lacking oxygen, protected Earth's surface from solar radiation, allowing these complex molecules to persist and evolve. Earth was no longer a molten, barren sphere. It had transformed into a world with oceans, atmosphere, and the potential for organic chemistry. The Earth-Moon partnership, forged in the aftermath of a cataclysmic collision, now provided the stability and conditions necessary for Earth to progress to the next stage of its journey. The Moon's influence was constant, shaping Earth's tides, moderating its climate, and creating a predictable environment. Together, Earth and the Moon formed a unique cosmic pair, their destinies intertwined as they orbited the Sun. As the early oceans continued to circulate and mix, the stage was set for the next chapter in Earth's story. A chapter that would see the formation of molecules, the birth of cells, and the dawn of life. The Earth-Moon system, forged in fire and shaped by water, had created a stable, nurturing environment, capable of supporting the earliest forms of life. The journey of Earth and its companion, the Moon, was far from over. In fact, it had only just begun. Chapter 5. The Moon's Influence on Early Earth. As Earth's transformation continued, the Moon played an indispensable role in stabilizing and shaping the young planet's environment. While Earth's oceans, atmosphere, and crust developed, the Moon's gravitational influence had far-reaching effects that would help create the conditions necessary for the emergence of life. Though silent and unchanging, the Moon's presence would be essential in moderating Earth's climate, creating tides, and even influencing the early development of ecosystems. One of the Moon's most profound influences on Earth was its role in stabilizing the planet's axial tilt. Earth's axis, which leans at an angle of about 23.5 degrees, is responsible for the seasons we experience as the planet orbits the Sun. Without the Moon, Earth's tilt would likely wobble unpredictably over time, leading to erratic changes in climate and extreme seasonal variations. However, the gravitational pull of the Moon exerts a stabilizing force on Earth's tilt, keeping it within a relatively narrow range. This consistency in axial tilt has allowed Earth to maintain a stable climate over millions of years, making it possible for ecosystems to develop and thrive. The Moon's gravitational pull also generated tidal forces that influenced Earth's oceans, creating the first tides. These tides, much stronger than those we experience today due to the Moon's closer proximity, caused the early oceans to rise and fall dramatically. Tidal action was not only a defining feature of Earth's early environment, but also a key factor in stirring the oceans, promoting the circulation of nutrients and minerals. This constant movement helped distribute chemical compounds essential for life throughout Earth's waters, creating a nutrient-rich environment ideal for the development of early organic molecules. As the oceans rose and fell with the tides, they interacted with the young planet's rocky surface, eroding land masses and carrying minerals into the seas. This process enriched the ocean waters, creating a complex chemical environment. The interplay between the tides and the ocean's chemistry led to the formation of tide pools along coastlines, shallow, isolated pockets of water that were subject to fluctuations in temperature, salinity, and chemical composition. These tide pools, with their unique blend of minerals and organic molecules, provided a fertile ground for the development of early chemical reactions, which would later contribute to the emergence of life. In addition to stirring the oceans, the Moon's tidal forces influenced Earth's geological activity. As the Moon pulled on Earth's surface, it created slight deformations in the crust, particularly in the regions closest to the Moon. This constant stretching and compressing of Earth's surface helped stimulate tectonic activity, a process that would lead to the formation of Earth's continents and mountains over geological timescales. The interaction between tidal forces and tectonic activity created a dynamic, ever-changing landscape on Earth's surface, which would eventually play a role in shaping the planet's diverse ecosystems. The Moon's influence extended beyond Earth's physical environment. It also affected the day-night cycle. Due to the gravitational interaction between Earth and the Moon, Earth's rotation slowed over time, lengthening the length of a day. In the earliest days of Earth, a single day may have lasted only a few hours, but as the Moon's tidal forces continued to exert drag on Earth's rotation, the day gradually lengthened. This slowing rotation led to a more regular and predictable day-night cycle, creating a rhythm that would become essential to biological processes and the development of early life. The Moon's role in creating predictable tidal cycles also had implications for the evolution of early life. As tides ebbed and flowed, early life forms which would eventually develop in Earth's oceans adapted to the changing conditions. This tidal rhythm created a natural cycle of exposure to nutrients, sunlight, and different temperature conditions, fostering an environment where chemical processes could become increasingly complex. Over time, this rhythm may have driven early organisms to develop adaptations to survive and thrive in the fluctuating environments created by tidal forces. The Moon's influence on Earth's climate, tides, and rotation created a stable environment that would remain consistent over millions of years, allowing life to emerge and evolve in an environment that was both challenging and nurturing. The Moon's presence offered a cosmic clock, providing regularity in an otherwise unpredictable universe. Its gravitational pull not only shaped Earth's physical environment, but also established cycles and patterns that would become integral to life's earliest forms. Beyond its influence on Earth's environment, the Moon also served as a shield, protecting Earth from excessive impacts by celestial bodies. During the chaotic early years of the solar system, Earth was frequently bombarded by asteroids and comets. The Moon, with its large size and proximity to Earth, acted as a kind of gravitational barrier, capturing or deflecting smaller objects that might otherwise have struck Earth. Evidence of these impacts can be seen in the numerous craters that cover the Moon's surface, scars from countless collisions that might have impacted Earth if not for the Moon's protective presence. As the Earth-Moon system continued to evolve, the Moon became an enduring companion in Earth's journey through the cosmos. Its presence allowed Earth to achieve a level of stability and predictability that is rare among planets. The Moon's influence was so profound that it became intertwined with Earth's identity, shaping the planet in ways that were essential for life's eventual emergence. The Moon was not merely a satellite orbiting Earth. It was a partner, a guiding force that helped mold the planet into a unique cradle for life. The relationship between Earth and the Moon, forged in the aftermath of a cataclysmic impact, became one of the most extraordinary partnerships in the solar system. Through gravitational forces and cosmic influence, the Moon transformed Earth from a chaotic, molten sphere into a stable, nurturing environment capable of supporting life. The early Earth-Moon system, with its rhythmic tides and stable climate, created the conditions necessary for life to develop and flourish, a cosmic collaboration that would shape the history of our planet. With the Moon's steady guidance, Earth's environment continued to evolve, setting the stage for even more profound transformations. The stable tides, regular day-night cycles, and predictable seasons allowed Earth's environment to maintain a balance that would be essential for the next chapter in its journey: the emergence of organic life. The Moon's silent influence would continue to be a guiding force as Earth progressed, its presence a testament to the power of cosmic relationships and the intricate dance of gravity and time. Chapter 6: Earth's Transformation into a Cradle for Life. With the Moon's stabilizing influence, Earth was able to develop a relatively stable environment, setting the stage for the next extraordinary transformation: the emergence of life. By this point, Earth had developed a rocky crust, vast oceans, and a thickening atmosphere, with the Moon's gravitational pull continuing to regulate Earth's axial tilt and drive powerful tides in its early oceans. These conditions, once hostile and turbulent, were now evolving into an environment that could support increasingly complex chemical interactions that would eventually lead to the formation of life's earliest building blocks. One of the most critical changes was Earth's cooling crust. As the planet continued to shed the intense heat left over from its formation, its outer layers solidified, forming a stable surface broken only by volcanic activity. These early volcanoes continued to release gases, further enriching the planet's atmosphere with carbon dioxide, nitrogen, water vapor, and trace amounts of other elements. This primitive atmosphere acted as a shield, protecting Earth's surface from harsh solar radiation and trapping enough heat to prevent Earth from freezing. Although the atmosphere was still inhospitable for life as we know it, it provided a crucial layer of protection that would enable organic molecules to form and persist. The constant volcanic activity also enriched Earth's surface with minerals and elements essential for life, such as sulfur, iron, and phosphorus. These minerals, combined with the elements dissolved in Earth's early oceans, created a nutrient-rich environment. In this dynamic setting, complex chemistry was unfolding. Hydrothermal vents, located on the ocean floor near volcanic ridges, released hot, mineral-laden water into the oceans, creating zones of unique chemical activity. These vent environments provided the extreme temperatures and pressure that allowed for the formation of complex molecules in Earth's young seas. At the same time, the Moon's gravitational influence created powerful tides that caused the oceans to rise and fall, stirring and mixing the water. This tidal movement helped to circulate minerals, gases, and other essential compounds throughout Earth's oceans. Tides created shallow pools along coastlines, isolated pockets of water that were regularly replenished by the ocean. These tide pools became natural laboratories where organic molecules could accumulate and interact, exposed to cycles of evaporation and concentration, providing a concentrated environment where more complex molecules could form. The continual mixing of ocean waters with minerals and organic compounds created a primordial soup, a blend of chemicals that would eventually lead to the formation of the first organic molecules. In this primordial environment, simple molecules began to combine and recombine, forming more complex structures. Amino acids, lipids, and nucleotides, the fundamental building blocks of life, began to take shape. The specific mechanisms through which these organic molecules assembled into complex structures are still a topic of scientific study, but the conditions of early Earth, with its rich oceans, volcanic vents, and tidal forces, provided the ideal setting for these molecular reactions. The interplay of temperature, pressure, and chemical diversity in hydrothermal vent regions likely drove the synthesis of some of these molecules, making it possible for them to survive and evolve into more intricate forms. As organic molecules accumulated and evolved, they began to exhibit properties that foreshadowed life. Some molecules formed lipid vesicles, tiny membrane-bound bubbles that could encapsulate other molecules, creating primitive compartments. These vesicles, precursors to cell membranes, helped protect and concentrate organic molecules, allowing for more complex chemical interactions within an enclosed environment. In these vesicles, organic molecules could interact without interference from the surrounding ocean, enabling reactions that might otherwise have been impossible. Meanwhile, Earth's atmosphere was also evolving. The continued volcanic activity released gases that increased the amount of carbon dioxide and nitrogen in the air. Though it was still devoid of oxygen, this atmosphere allowed sunlight to penetrate and warm Earth's surface, driving further evaporation and condensation in the water cycle. Lightning, generated by the friction between particles in volcanic ash clouds and rain, became a source of energy, providing additional catalysts for chemical reactions in the atmosphere and oceans. The energy from lightning strikes and the sun's UV radiation fueled reactions in Earth's atmosphere, helping to produce simple organic molecules that would rain down into the oceans, adding to the already rich chemical mix. Over millions of years, these molecules continued to evolve, interacting in increasingly complex ways. Some began to develop the ability to self-replicate, a crucial step in the origin of life. Through processes like natural selection, these self-replicating molecules gradually evolved into structures that could store information, transfer energy, and perform basic functions. Among these early forms of self-replicating molecules were primitive RNA molecules, which could copy themselves and transmit information, setting the foundation for life's earliest genetic material. These self-replicating molecules eventually assembled into what scientists believe were the first protocells, small, membrane-bound structures capable of basic metabolic functions. Protocells were not yet fully alive by modern definitions, but they had the essential characteristics that would eventually lead to cellular life. Encapsulated within lipid membranes, these protocells could concentrate nutrients, expel waste, and perform simple chemical reactions, marking the beginning of biological complexity. The Moon's influence continued to shape this evolutionary process. Its strong tidal forces created environments where protocells could be periodically exposed to sunlight, facilitating energy absorption and encouraging biochemical reactions within them. Over time, protocells adapted to the rhythmic cycles of tides and day-night variations, integrating these external cues into their metabolic processes. The Moon's gravitational pull, which moderated Earth's tilt and created predictable seasonal patterns, provided an environment where these emerging life forms could adapt to the natural rhythms of the planet. With the formation of protocells, Earth was well on its way to becoming a cradle for life. Though these early life forms were simple, they represented a monumental leap in the evolution of complexity on Earth. They provided the foundation for all future life, introducing the ability to replicate, metabolize, and respond to environmental changes. This transformation from complex molecules to protocells was a pivotal step in Earth's journey, as the planet moved from a chemical-rich environment to one capable of sustaining biological processes. As these protocells diversified, they continued to adapt to Earth's oceans and environments. Over millions of years, the interaction between protocells, the oceans, and the atmosphere would drive the evolution of more complex organisms. These early cells would become the ancestors of all life on Earth, initiating the long and diverse history of biological evolution that would lead to the rise of plants, animals, and eventually, intelligent life. In this cosmic journey, Earth had transformed from a molten, volatile sphere into a stable world with oceans, atmosphere, and the first building blocks of life. The Earth-Moon relationship, forged through the impact that created the Moon, was integral to this transformation. The Moon's influence over Earth's tides, axial tilt, and climate stability was critical in creating an environment where life could emerge. The Earth-Moon system had set the stage for one of the most extraordinary processes in the universe, the evolution of life. As Earth continued to cool and stabilize, and as protocells adapted and diversified, the planet entered a new phase of its journey. With the building blocks of life firmly established, Earth was on the brink of a biological revolution that would shape its landscapes, atmosphere, and ecosystems in ways unimaginable at the time. The Earth-Moon partnership, born from a cataclysmic collision, had created the conditions for life, forever intertwining their destinies in a cosmic story of transformation, adaptation, and evolution. Chapter 7. The Moon's Long-Lasting Legacy. As life began to emerge and evolve on Earth, the Moon's presence remained a constant, continuing to influence the planet in ways that would prove essential to the survival and development of ecosystems. Over billions of years, the Moon's gravitational pull had stabilized Earth's environment, shaping its physical features, climate, and rhythms. While life adapted to Earth's day-night cycles, seasons, and tides, the Moon's long-lasting legacy became inseparable from the story of life on Earth. One of the moon's most profound effects was its role in creating stable seasons. Earth's axial tilt, the angle at which the planet leans as it orbits the sun, is responsible for the seasonal changes we experience throughout the year. Without the moon, Earth's tilt would likely vary erratically due to gravitational influences from other planets and celestial bodies. These shifts in tilt could have resulted in extreme climate changes, with regions shifting from tropical to polar climates over relatively short timescales. The moon's stabilizing force kept Earth's tilt relatively steady, giving rise to predictable seasonal patterns. These stable seasons were vital for the development of complex life. As Earth's climate remained predictable over long periods, organisms could adapt to seasonal cycles, evolving traits that allowed them to thrive in different climates and conditions. The moon's gravitational pull provided the consistency that enabled plants and animals to evolve with the rhythms of the seasons, supporting ecosystems that relied on stable conditions to flourish. Forests, grasslands, deserts, and polar regions became distinct biomes, each adapted to the specific climate patterns created by Earth's steady tilt. The moon's influence extended to Earth's oceans and tides, which were crucial in shaping coastal and marine ecosystems. Tidal forces, created by the moon's gravitational pull, caused the oceans to rise and fall in predictable cycles. These tides affected not only the ocean waters but also the land, creating intertidal zones along coastlines where land and sea met. The intertidal zone, subject to regular flooding and exposure due to the tides, became a unique and highly dynamic environment. In these intertidal zones, a wide range of organisms adapted to survive the changing conditions of the tides. Seaweed, barnacles, crabs, and fish developed specialized traits to cope with being submerged in water during high tide and exposed to air during low tide. These organisms relied on the moon's tidal rhythms to guide their behaviors, from feeding and breeding cycles to migrations. Over time, the intertidal zones became bustling hubs of biodiversity, demonstrating the moon's enduring legacy in shaping life on Earth. Beyond the intertidal zones, the moon's influence on tides also affected the deep oceans. Tidal forces created currents that circulated nutrients and oxygen throughout the ocean, providing the essential elements needed for marine life to thrive. These currents, stirred by the moon's gravitational pull, helped distribute nutrients from the ocean floor to the surface, supporting the growth of plankton, the foundation of the ocean's food chain. In this way, the moon's influence extended deep into the ocean, creating a stable and nutrient-rich environment for marine ecosystems to flourish. The moon's stabilizing effect on Earth's rotation and climate also contributed to the development of circadian rhythms, biological processes that follow a roughly 24-hour cycle. As life on Earth adapted to the day-night cycle, organisms evolved internal clocks that synchronized their behaviors with the rhythms of the planet. Plants began to open their leaves in the morning and close them at night, while animals developed sleep-wake cycles based on the day's light patterns. These circadian rhythms became deeply ingrained in life on Earth, influencing everything from cellular functions to complex behaviors. The moon's gravitational pull also influenced Earth's tectonic activity, although to a lesser degree than its effects on tides and climate. The constant tugging of the moon created small stresses in Earth's crust, contributing to the movement of tectonic plates. This process, combined with the heat generated by Earth's core, helped drive volcanic eruptions, the formation of mountain ranges, and the shifting of continents. Over millions of years, tectonic activity reshaped Earth's surface, creating diverse landscapes and habitats that would become home to a wide variety of life forms. As life continued to evolve, the moon's presence remained an unwavering constant in the sky. Ancient civilizations, observing the moon's predictable cycles, developed calendars based on its phases, using it to mark time and seasons. The moon's role in Earth's history became deeply woven into human culture, mythology, and science. It was a source of wonder, inspiration, and guidance for early humans, symbolizing both mystery and reliability. Many ancient cultures associated the moon with deities, marking it as a symbol of fertility, transformation, and protection. The moon's influence on Earth is also evident in its ability to shield the planet from some of the solar system's dangers. During the early years of the solar system, Earth was frequently bombarded by meteoroids and asteroids. The moon, with its own gravitational field, acted as a partial barrier, absorbing or deflecting smaller objects that might have otherwise struck Earth. The craters that cover the moon's surface are evidence of these impacts, a testament to the moon's role as Earth's silent protector. By absorbing some of the impact of meteoroids, the moon helped to shield Earth, preserving the stability necessary for life's evolution. The moon's long-lasting legacy can also be seen in its gradual retreat from Earth. Due to the exchange of gravitational energy, the moon is slowly drifting away from Earth at a rate of about 3.8 centimeters per year. This process, although gradual, has implications for Earth's tides and rotation. As the moon drifts farther away, its tidal influence on Earth decreases slightly, and Earth's rotation gradually slows. While the effects of this retreat are imperceptible on a human timescale, over millions of years, it will continue to shape Earth's relationship with its lunar companion. As humanity entered the age of exploration and scientific inquiry, the moon became the first celestial body to which humans would aspire to travel. In 1969, humans set foot on the moon for the first time, a monumental achievement that underscored the connection between Earth and its nearest neighbor. The samples brought back from the moon provided scientists with valuable insights into its origins, confirming that the moon shared a common history with Earth, formed from the remnants of a cataclysmic collision billions of years ago. Today, the moon remains a constant in our skies, a symbol of the cosmic forces that shaped our planet and a reminder of the early events that enabled life to flourish on Earth. Its gravitational pull continues to guide Earth's tides, influence its rotation, and maintain its tilt, silently shaping the rhythms and cycles that sustain life. The moon's legacy, embedded in every tidal wave, seasonal change, and day-night cycle, is a testament to the powerful relationship between Earth and its lunar companion. As Earth and the moon continue their cosmic journey, the moon's influence endures, a stabilizing force that has guided Earth through billions of years of evolution. The moon, once part of Earth and forged in the fires of a great impact, remains Earth's closest partner in its journey through the cosmos. Its legacy will persist as long as life exists on Earth, a silent yet ever-present witness to the unfolding story of our planet. Chapter 8. Earth's Transformation into a Cradle for Life. With the moon's stabilizing influence and Earth's environment settling into a more balanced state, the stage was set for an extraordinary transformation. Earth's oceans, atmosphere, and rocky surface had evolved to support increasingly complex chemical processes, laying the groundwork for the first forms of life. Over billions of years, the planet had transformed from a molten, chaotic sphere into a world with oceans, land masses, and an atmosphere capable of sustaining organic chemistry. Earth had become a cradle for life, ready for the next phase in its evolutionary journey. One of the most critical aspects of Earth's transformation was the development of a stable atmosphere. Through constant volcanic activity, gases such as carbon dioxide, nitrogen, and water vapor had been released into the atmosphere, creating a layer that shielded Earth from the harsh radiation of the sun. This primitive atmosphere also helped to trap heat, keeping Earth's surface warm enough for liquid water to exist. This balance between atmospheric gases created a temperate environment that would prove crucial for life's development. With the atmosphere in place, rainfall began to fill the planet's low-lying areas, forming vast oceans. These early oceans, enriched with dissolved minerals and chemicals, provided the ideal conditions for the formation of organic molecules, the building blocks of life. Simple compounds formed through reactions in the atmosphere and delivered by meteorites accumulated in the oceans. Over time, these compounds began to interact, forming more complex molecules like amino acids, lipids, and nucleotides, which would eventually become the foundation of life. Within these nutrient-rich oceans, hydrothermal vents on the ocean floor played a crucial role in the emergence of life. These vents released hot, mineral-laden water, creating unique environments where chemical reactions could take place under extreme conditions. The heat from the vents, combined with the variety of minerals and gases, provided the perfect environment for the synthesis of complex molecules. In these deep-sea environments, simple molecules combined to form more sophisticated structures, leading to the creation of the first organic compounds with the potential for self-replication and metabolism. At the same time, the Moon's gravitational pull continued to influence Earth's environment. The strong tides created by the Moon's proximity stirred Earth's oceans, mixing minerals, gases, and organic molecules throughout the water. These tidal movements also created isolated tide pools along coastlines, where water would evaporate, concentrate, and replenish in regular cycles. These changing conditions encouraged the formation of more complex organic molecules, as compounds were exposed to different temperatures, concentrations, and chemical environments within tide pools. In these early oceans, organic molecules eventually began to develop into protocells, small membrane-bound structures that could enclose other molecules, providing a primitive form of cellular organization. These protocells were not yet alive by modern definitions, but they represented an important step toward life. Encapsulated within lipid membranes, these protocells could concentrate nutrients, expel waste, and perform basic chemical reactions, offering the beginnings of metabolism and cellular structure. With Earth's environment gradually stabilizing, these protocells began to exhibit behaviors that foreshadowed life. Some protocells evolved the ability to self-replicate, using simple molecules from their environment to duplicate their structures. This self-replication marked a pivotal moment in Earth's history, as it introduced the concept of heredity and the potential for natural selection. Over generations, these protocells diversified, adapting to different environmental conditions and evolving into more complex forms. As these early life forms adapted to Earth's environment, they evolved strategies to harness energy from their surroundings. Some developed the ability to perform photosynthesis, a process that allowed them to capture sunlight and convert it into chemical energy. This ability to transform sunlight into energy had profound implications for Earth's atmosphere and ecosystems. The oxygen produced by photosynthetic organisms began to accumulate in the atmosphere, transforming it from a toxic, anaerobic environment into one capable of supporting aerobic life forms. This great oxygenation event, driven by early photosynthetic organisms, changed the composition of Earth's atmosphere forever. Oxygen, once a rare gas, became a significant component of the atmosphere, eventually leading to the formation of the ozone layer. This layer provided further protection from the sun's harmful ultraviolet radiation, enabling life to colonize Earth's surface as well as its oceans. Oxygen also enabled more efficient metabolic processes, allowing organisms to generate more energy and supporting the evolution of more complex life forms. As life diversified and adapted to Earth's changing environment, it spread across the planet's oceans, thriving in the nutrient-rich waters and along coastlines. The Moon's influence continued to shape Earth's tides, creating habitats that organisms adapted to. These tidal zones, where land met sea, became hotspots of biodiversity, with organisms developing unique adaptations to cope with fluctuating water levels, salinity, and sunlight exposure. The cycles of tides and seasons, influenced by the Moon's gravitational pull, provided a natural rhythm that life on Earth evolved to follow. With each passing eon, Earth's biosphere grew more diverse, complex, and resilient. The oceans teemed with microscopic life, forming the base of a vast food web that supported increasingly complex organisms. Some organisms began to explore new niches, venturing onto land where they encountered different challenges and opportunities. The evolutionary pressures of these new environments drove the development of new traits, leading to the rise of plants, animals, and eventually a rich variety of ecosystems. Throughout this transformation, the Moon remained a silent partner in Earth's journey, its influence woven into the very fabric of life on Earth. Its gravitational pull created tides, which stirred the oceans and influenced the movement of nutrients. Its stabilizing force on Earth's axis created a predictable climate, supporting the development of ecosystems across the globe. And its presence in the night sky served as a constant guiding force, shaping Earth's physical and biological rhythms in ways both visible and unseen. The relationship between Earth and the Moon had transformed Earth from a molten, lifeless sphere into a thriving planet, a cradle for life in a universe that appeared otherwise barren. The Moon's role as Earth's stabilizer and companion was essential in creating an environment where life could not only emerge, but also evolve and diversify. This unique partnership set Earth apart, allowing it to become a world teeming with life, from the simplest microbes to the most complex ecosystems. As Earth's journey continued, life evolved and adapted, creating a rich tapestry of biodiversity that covered the planet. From the depths of the oceans to the peaks of mountains, life spread to every corner of Earth, guided by the Moon's steady influence. This remarkable journey, from protocells to ecosystems, was a testament to the power of cosmic forces and the enduring partnership between Earth and its lunar companion. Today, the legacy of Earth's transformation into a cradle for life remains evident in every living organism, from the tiniest microbe to the largest mammal. The Moon's influence continues to shape Earth's environment, providing stability, balance, and rhythm to a planet that would be unrecognizable without it. The Earth-Moon system, forged in the aftermath of a cosmic collision, had achieved something truly extraordinary. It had created a home for life, a sanctuary in the vastness of space where life could thrive and evolve across the ages. Chapter 9. The Legacy of Earth and Moon. The relationship between Earth and its moon is one of the most enduring partnerships in the solar system. Over billions of years, the moon has been more than just a satellite orbiting Earth. It has been a stabilizing force, a cosmic shield, and a guiding influence on the rhythms of life. This partnership, born from a cataclysmic collision, has shaped Earth's environment, guided the development of life, and left a legacy that continues to impact our world today. One of the moon's most remarkable contributions is its role in stabilizing Earth's axial tilt. Without the moon, Earth's axis might wobble chaotically due to gravitational influences from other planets. This wobbling would have led to extreme fluctuations in climate, with regions on Earth experiencing drastic changes between tropical and polar conditions. The moon's gravitational pull has kept Earth's tilt relatively stable, allowing for predictable seasonal cycles. This stability has been essential for the development of ecosystems that rely on consistent climate patterns. The presence of the moon has made Earth a planet where environments can sustain life over long periods, providing a stable climate that has supported the evolution of diverse species. The moon has also been crucial in creating tides, one of the most dynamic and influential features of Earth's environment. The gravitational pull of the moon causes the oceans to rise and fall in regular cycles, shaping coastlines and creating unique habitats. These tidal zones where water meets land became rich and diverse ecosystems filled with organisms adapted to changing conditions. The daily ebb and flow of the tides have created habitats where life has thrived, from the smallest microbes to complex plants and animals. Coastal species have evolved to depend on the tides for feeding, breeding, and migration, building entire ecosystems around the rhythmic influence of the moon. In addition to influencing tides and climate, the moon has served as a shield for Earth, absorbing impacts from meteoroids and asteroids. During the early years of the solar system, collisions with space debris were common. The moon's large size and close proximity to Earth meant it often acted as a gravitational barrier, capturing or deflecting objects that might otherwise have struck Earth. The surface of the moon, marked with countless craters, serves as a record of its role as a protector. By absorbing the force of these impacts, the moon helped preserve the stability of Earth's surface, reducing the frequency of catastrophic events and allowing life to flourish without constant disruption. Over time, the moon's influence on Earth's rotation has also been profound. The gravitational interaction between Earth and the moon creates tidal friction, which gradually slows Earth's rotation. In the early days of the Earth-Moon system, a single day on Earth may have lasted only a few hours. But, as the moon's gravity exerted a steady pull on Earth, it gradually lengthened the planet's rotation period, giving us the 24-hour day we experience today. This longer day-night cycle has influenced the circadian rhythms of life on Earth, shaping the daily patterns of activity for countless species. From the opening of flowers to the sleep cycles of animals, life on Earth has adapted to the natural rhythm created by Earth's rotation, a rhythm that the moon has helped establish and maintain. The legacy of the moon extends beyond its physical influence. It has become deeply embedded in human culture, mythology, and science. Throughout history, the moon has been a source of fascination, inspiration, and mystery. Ancient cultures used the moon to mark time, developing lunar calendars to track the months and seasons. The moon was often associated with gods and goddesses, symbolizing fertility wisdom, and transformation. In many cultures, the phases of the moon became symbolic of life's cycles, representing birth, growth, decline, and rebirth. The moon's regular and predictable cycles were a constant in the sky, a reminder of order in a changing world. In more recent history, the moon became a focal point for humanity's scientific exploration and technological ambition. In 1969, humans set foot on the moon for the first time, a momentous achievement that symbolized humanity's desire to understand and explore the cosmos. The Apollo missions not only demonstrated our technological capabilities, but also provided a deeper understanding of the moon's composition, origin, and relationship with Earth. The samples and data collected from the moon confirmed the giant impact hypothesis, showing that the moon shares a similar composition to Earth's outer layers, a result of their shared history. Today, the moon continues to captivate scientists, astronomers, and explorers. Its proximity and familiarity make it an ideal target for further exploration, and its potential as a base for space exploration is being considered by space agencies and private companies alike. As humanity looks to explore other planets, the moon remains a symbol of the frontier, a reminder of Earth's place in the universe and the possibilities that lie beyond our world. The moon's legacy as a constant companion to Earth is a testament to the interconnectedness of celestial bodies and the profound impact they can have on each other. The Earth-Moon system is unique in the solar system, a partnership that has endured for billions of years. This cosmic relationship has given rise to a world teeming with life, a stable environment where ecosystems can flourish, and a haven for human civilization. The moon's influence on Earth is felt in every tide, every seasonal change, and every day-night cycle. It is embedded in the rhythms of life, in the migrations of animals, the cycles of plants, and the cultural expressions of humanity. As we continue to study and explore the moon, we gain new insights into Earth's history, evolution, and place in the cosmos. The moon serves as a reminder of the forces that shaped our planet, the delicate balance that sustains life, and the vastness of the universe beyond. The legacy of Earth and the moon is a story of resilience, transformation, and partnership. A story that has been written in the stars and the waves, in the tides and the seasons. This legacy endures as a testament to the remarkable forces that have shaped our world, and the enduring bond between Earth and its closest companion. As Earth and the moon continue their journey around the sun, they carry forward a shared history, a legacy of cosmic transformation that has made Earth a unique cradle of life in a vast, largely unknown universe. The moon will remain in our skies, a silent partner and witness to Earth's journey, a symbol of the powerful relationships that define the fabric of the cosmos. The legacy of Earth and the moon is a story still unfolding, a reminder that the forces that shaped our planet are part of a greater tapestry that extends far beyond our world. The story of Earth and the moon is one of cosmic transformation, a tale that spans billions of years, filled with moments of creation, upheaval, and stability. From a cataclysmic collision to the formation of oceans, atmosphere, and life. Earth's journey has been shaped and guided by its relationship with the moon. Together, these two celestial bodies have carved out a unique place in the solar system, a stable and nurturing environment that became home to the incredible diversity of life we see today. The moon has been more than a silent observer. It has been an active partner, shaping Earth's physical environment and creating conditions that would allow life to flourish. Its gravitational pull has provided stability, creating tides that stirred the oceans and supported early ecosystems. Its influence on Earth's rotation and axial tilt has given rise to predictable seasons, allowing life to adapt to regular cycles. The Moon's presence has been essential to Earth's transformation, providing a balance that has supported life's evolution across eons. This partnership has also been woven into the cultural and spiritual fabric of humanity. The Moon's cycles have inspired myths, guided calendars, and become symbols of change, growth, and renewal. For ancient civilizations, the Moon represented both mystery and continuity, a constant in the sky that connected them to the greater universe. In modern times, the Moon has become a destination for exploration and discovery, a stepping stone for humanity's journey beyond Earth. The legacy of Earth and the Moon is a testament to the intricate dance of gravity, time, and cosmic forces that has shaped our world. The Moon, once part of Earth and forged through a collision of unimaginable force, has become an enduring companion, a guiding light in the night sky. Its influence is felt in every tide, every day-night cycle, and every shift in the seasons. Together, Earth and the Moon continue their journey around the Sun, their fates bound by the forces that brought them together billions of years ago. As we look to the future, the Moon remains a source of inspiration and a reminder of our place in the universe. It speaks to the resilience of life, the beauty of cosmic relationships, and the power of transformation. The story of Earth and the Moon is far from over. It is a story that continues to unfold with each orbit, each sunrise, and each tide. This journey, born from chaos and guided by balance, stands as one of the universe's most profound legacies, a legacy of life, stability, and the enduring bond between Earth and its Moon.